some. Okay, so hello. Welcome to the session on spatial statistics. We have 4 speakers for now, so I hope we will enjoy. And because Brian Fuentes have some issues with the microphone, and I don't see Nicholas Kushnik, which is second speaker. So can I ask you, artists,
Yeah,
if you are able? So
yeah, sure.
just feel free to share the screen and you can start.
Okay, so going to share my screen. Just wait. Okay,
Perfect. Yeah, we can see it.
it's
Thank
okay.
you.
Yeah.
Yeah.
So thank you very much, all of you, for being here in this virtual session, attending this session virtually. My name is Aritz from the Public University of Navarra in Spain, and the title of my presentation is Big DM, an R package to fit scalable Bayesian, spatial, and spatiotemporal disease mapping models for high-dimensional data. So the structure of the presentation will be as follows. In first place, I will introduce the problem that we want to solve, which essentially is to propose an scalable method to estimate mortality or incidence risks in high-dimensional aerial data. I will present the main characteristics of our R package BigDM that has been developed with that purpose, briefly describing the methodology behind the package and also showing you some vignettes and examples that can be or that are reproducible. And finally, I will conclude with some conclusions and new improvements that will be available soon in the next versions of the package. So I think that we are all aware that modern geostatistical data typically involves large data sets collected from a variety of sources. And consequently, the development of new techniques and computational algorithms to analyze this massive data, it's of crucial interest in many fields such as remote sensing, geoscience, or epidemiology, among others. So disease mapping is the field of spatial statistics that deals with aggregated count data from non-overlapping aerial units, focusing on the estimation of the geographical distribution of a disease and its evolution in time. So the 3 main inferential goals in disease mapping are to provide accurate estimates of mortality or incidence risks, to unveil the underlying spatial and spatiotemporal patterns, and to detect high risk or hotspot areas. So the problem is that classical risk estimation measures, such as crude rates or standardized mortality ratios, are extremely variable when analyzing very rare diseases or low populated area. So this makes necessary the use of statistical models to smooth risk, borrowing information from spatial or temporal neighbors. For example, here in this map in the left, you can see a typical map of representation of a standardized mortality ratio, which is just a quotient between the expected number of cases and observed number of cases. If an area has a standardized mortality ratio higher than 1, we say that that area has a risk greater than the whole study region. And conversely, if it has a risk, a standardized mortality ratio lower than 1, it is a low risk area. But the problem is that here we are not able to see or to detect any geographical distribution or any spatial pattern of this disease. In contrast, if we use statistical models, we can obtain this kind of smooth risk surface estimates where we can somehow make hypotheses about the etiology of the disease or have an idea what's the spatial pattern of the disease that we are analyzing. So probably the most used models in the disease mapping literature are the spatiotemporal CAR models proposed by NordHealth, even that there are other approaches such as, for example, reduced rank multidimensional p-splines or many other models. But despite the enormous expansion of modern computers and the development of new software, to make full Bayesian inference, because most of these models are estimated from a fully Bayesian inference. Dealing with massive data is still computationally challenging. So a few time ago, we asked ourselves the following question. Are these smoothing methods appropriate when analyzing very large spatiotemporal datasets? And we think that the answer is no, mainly because of two main problematic aspects. The first one is the computational time and computational resources that are needed to estimate these models, because I would say most of these models, or all of them, are built on the idea of spatial and temporal correlation. So in some points of the estimation approach, we will need to use the covariance or precision matrix to inverse these matrices to compute Cholesky decomposition or Eigen decompositions. And if these matrices are really, really, really large or has a high dimension, the computational cost of these operations will be sometimes prohibitive. And the second problematic aspect is that car models induce the same degree of smoothness or the same degree of spatial dependence to the wall adjacency graph. That is, we are assuming the same spatial dependence in this area in the north or in this area in the south, and that's probably not realistic in a real data analysis or real analysis. So what we have done is to develop some modeling proposals that are scalable and non-stationary Bayesian models to analyze this high-dimensional data. And these models are already implemented in the R package BigDM, which is available at CRAN. I think that's from February. And we also have a GitHub repository. I don't know if you can see it. I hope so. This is a repository where we have some kind of development version of the package. Okay, I will come here again later. All the modeling approach is based on the idea of divide and conquer. So I will explain it now with more detail. But what we are doing is dividing the spatial domain, and in each of these partitions, we are fitting independent spatial or spatiotemporal models. So all the methodology is explained in these two papers. The first one is already published in Spatial Statistics. The second one is still on archive, but I hope that it will be published soon. Sorry. All the inference in this package is based on the well-known integrated nested Laplace approximation technique, or INLA technique, through the R-INLA package. I hope most of you will know this very, very used package. And also, we have incorporated some functions and arguments based on the future package, so that parallel and distributed computation strategies can be performed to speed up computations, depending on the computational resources of the user, of course. So I will try to briefly describe the modeling approach, which is based on three main steps. In the first step, we divide the region of interest into different subdomains. Then we estimate local spatiotemporal models using INLA. And finally, we have to merge the results, because you will see now that in some cases, we will have more than one estimation for an area. So these results have to be merged into a unique INLA object, so that we can apply the usual functions of the INLA package. So how are we going to divide the data? Or why are we going to divide the data? Because, as I told you before, instead of considering a global random effect whose correlation structure is based on the whole spatial adjacency graph, we are proposing to divide this data so that we can fit these local models using different hyperparameters or whatever parameters have the model. So usually, or the best way to do these partitions will be using administrative divisions, such as provinces, states, or local health areas. But the package also has a series of functions in order to do some random partitions if the user do not have this kind of information. I think that this random partition are made in a regular grid, but it can be made in another way. Sorry, here. So we are defining two types of models. The first model is the simplest one. We are assuming independence between areas belonging to different areas. So we are fitting independent models, but that has a problem, and this is that we can have border effects, because we are assuming that two areas that belongs to different subdomains are independent, and that's not usually realistic. So we can somehow add neighbors. I think in this picture we can see it more clearly. This region is divided into 4 subdomains. We can fit a model in each of these subdomains, or we can add neighboring areas, these blue areas or second order neighboring areas, in order to obtain better estimates for the areas that are located in the border, because we are adding information from neighboring areas to the estimation. Okay, these car models induce smoothing using neighboring areas. Then, as I told you, we have to merge the results. If we are fitting the decision model, we just have to join the relative risk estimate. But if we are using this model that we have seen in several simulation studies and several data analysis, that is the best one, we have to combine the posterior distribution of those areas that are estimated in more than one model, because we can have more than one posterior estimate for each area, but we only want one. So we are proposing two different strategies. The first one is to compute mixed distributions of the posterior probability density functions, and the other one is to use the original relative risk estimate of the area, that is the estimation in the model that it's really belonging. So there are several functions in the package in order to make these spatial partitions, to merge the results. But I have outlined these two main functions that somehow combines all of them. So the main function of the library is the car in-la functions to fit the spatial car models, and the STCar in-la function to fit spatiotemporal car models. Okay. And as I said you, there are several vignettes that we can read it to better understand how to use the package. So the first vignette is focused on spatial models. Here you can read some methodological aspects, how the models are defined, the prior distribution, some aspects about inland. Here are different examples of how can we use the functions of the package with the references at the end. Also, we have a similar vignette using the STCar function to fit spatiotemporal models. And we have also included a shorter vignette in order to explain how can we use the future package to perform both parallel or distributed computations, because we can fit these models using different in parallel, I mean, in different R sessions, but we can also distribute these models in a computational cluster or high performance computing or wherever the user have in his university, or so the user can adapt the computation strategy. So in conclusion, we have developed a package that implements this kind of scalable Bayesian models. All the methodology is based on the idea of divide and conquer, which is a strategy that has been extensively used in other contexts, such as, for example, machine learning. And we have seen that adapting this idea to the context of disease mapping is very appropriate, because it is a natural and simple strategy. The larger the spatial domain is, the less likely is that data are stationary across the whole map. And of course, it provides us, as we are providing a scalable method, the computational time and CPU or RAM memory usage is reduced substantially. So the package is built in the top of these other two packages, no? The INLA estimation strategy and the future package to make the distribution of the modeling approach. And I want also to tell you that we are now currently working on extending also this methodology to fit ecological regression models, that are models that also include covariates that could be potential risk factors, and also to multivariate disease mapping models in which several diseases are jointly analyzed. So these are some of the references. There are all of them also in the vignettes, and this is our funding. So if someone needs more information, can contact me directly, or just simply go to the GitHub page and make some pull request or wherever you need. So this is all. I'm going to stop sharing my screen.
Okay, thank you very well. And you can send your messages to Q&A if you have any questions. Thank you for the good timing.
Yeah.
It's perfect. Okay, so not questions so far, but we can wait a few seconds.
Okay.
I think next speaker will be Brian, if it's okay with your microphone. Brian, are you here? Okay, nothing from Brian. Yeah, okay, so I can see one question. Wonderful talk. Are the slides available?
Yes, I can put it here, or I don't know. Is here any place to share my presentation?
You can. We can see the recording after, so you can like watch the presentation again. And I think you can add some documents to the session
Okay, I
in
will try.
the previous in the lobby. So maybe you can try. Another question. A nice talk, thanks. Can you also use the package to model origin-destined relations? So kind of for them observations.
Not at the moment, but if there are models that can somehow adapt it to this kind of data, because we are dealing with aggregated count data. So if these kind of models are already derived, we can adapt it to our scalable proposal and incorporate it in the package, but at the moment, no.
Okay, thank you. So I think our time is up for now. So thank you very much for the presentation again.
Thanks.
So Brian, can you hear us? Okay, and others, Nicholas and Crystal, are you here?
Hey, does my mic work? It should.
Okay, so yeah, we can see you and hear you.
Yeah, I hope my share screen works. It should.
Yeah, so you can share your screen and you can
Oh no.
start if you are fine. So Nicholas Kushnik.
Okay. So I'm assuming you can see what's happening. A huge loop.
Yeah, it's working good.
Okay.
Thanks.
Well, thanks for showing up, everyone. I'll be talking about Bayesian spatial econometrics and specifically a software architecture for it and our implementation and some applications. I'm very sorry if my mic is noisy or there's noise in the background. I'm in a hotel room and I was able to check in early, which is great, but the noise is not so great. So sorry for that, and stop me if it gets unbearable. So maybe to motivate this, first, I'm assuming you have an idea about spatial econometric models, but these are just kind of network models where you know the location and you assume you know the connectivity. So you have a very parsimonious way of estimating these network models and having a look at spillover effects. That can be very limiting, and so Bayesian approaches play a crucial role in developing them further. Examples include Bayesian model averaging to filter out uncertainty around the exact model, hierarchical models where you have different layers. Maybe something is happening at the municipality level, but they're still related to a state level or the national level, for example. Another kind of important issue that's also related to model averaging and hierarchical models is the treatment of connectivity. That can also work quite well with Bayesian methods. And last but not least, they've been used to model spatial econometric models with limited dependent outcomes. Now, while there's a lot of progress on the method side, they're very rarely used in applied work. And I think that's due to a lack of software in one regard, right? So Bayesian spatial software for spatial econometric methods, it needs to accommodate both the flexibility of Bayesian hierarchical modeling as well as the peculiarities of spatial econometrics, right? So domain-specific packages like SpatialRec, they're kind of focused on frequentist estimation, and that's basically where they come from. So they're constrained in their flexibility. Other packages like the MATLAB toolbox is not as available, but that includes a lot of code and is not that flexible, right? So it's still kind of script-based, how most of it is done. And so the cookie cutter Bayesian modeling software like STAN and so on, they can be very inefficient and ineffective for spatial models because, well, the main issue is probably the Jacobian computation, which happens at each iteration in STAN, but we don't need to do that. So they've been found to be ineffective, even though they can use some really cool samplers and so on. Now, a brief overview about this talk. So I will present the software architecture for this. It's supposed to be powerful and extensible, so it should include a lot already, but it should be straightforward to extend parts of it. It should still be accessible to users, and it should be easy to maintain, right? So we want to reduce the amount of code. We want to have good tests and so on. We don't want a bloated mess where everything is just iterated again and again. I will also demonstrate briefly an implementation in the BSREC package, which is on CRAN. And if there's time, I may also briefly talk about some applied results in this paper that on one hand show why Bayesian models are nice, and on the other hand, why there's an urgent need for tried and tested software and like stepping away from the script-based research and work that's happening at the moment. So first, let's do a bit longer of a recap of spatial econometrics and Bayesian estimation, but still it's very brief. I'm hoping that you have at least some kind of grasp. So the general spatial econometric models with all three legs of the dependent, the explanatories, and the errors it looks like this. In practice, you use one or two of these at a time usually. And the trick is basically this matrix W. It's n times n, so for each observation usually, and it induces a spatial lag. You can think of this like in time series models where today is related to yesterday. Here it's the same, but we have an additional dimension, right? So maybe I'm related to the presenters before and after me, right? And yeah, also like in a classroom, for example, students that sit close to each other, they may be related. That's encoded in W. And yeah, we have these three kinds of lags. So one, it's autoregressive, and then there's spatial interference, or also called a local lag, because it's just one step further via the explanatories, and then there's the error term, of course. Now, Bayesian estimation of these models generally works with Monte Carlo Markov chain sampling methods. These, in general, they work by, we isolate conditional posteriors, right? So this the posterior of maybe this autoregressive term lambda, conditional on, of course, the data, but also the other parameters. And then we can draw from that, and if we do that repeatedly, we arrive at the full posterior. So with that in mind, it helps to reinterpret the spatial model. So, for example, just the autoregressive one, as a nested linear model with this latent variable z here. It's just plain old what you learn at the start of a statistics course. And then you have this spatial filter here. I denote it as S. That's a function of lambda, and it's conditional on W. And we filter that over our linear model. That will be useful for the implementation. So let's talk about the software architecture. Now, the first critical observation is that the MCMC sampler, it's basically fully characterized by a certain state, right? So the parameters are at this and that level, and rules to update this state, right? So, okay, we have some data. How do we change the state? Or basically, how do we draw a new from exactly this posterior? So it's an infinite state machine. We just have the parameters and rules to update it. And to actually use such a state machine, we want to update it repeatedly and store the state, right, in memory. So we have posterior draws. Now, for interacting with this, it also helps to have an interface, right? So we want to feed in data, feed in our priors, and maybe adjust the sampling steps. So we have some inputs in here that go via this interface, and maybe you have a matrix or some kind of storage for this, but you also want this to be easily analyzed with, for example, plotting methods and so on. Now, based on this whole notion, I derive a prototype-based object-oriented system. The idea is that we depart from a simple linear model with some small adjustments like the priors or computational tweaks and so on, but also further extensions. For example, a local spatial lag. So if we provide this W matrix, we can automatically blow up this simple linear model to have a local spatial lag. But also spatial filters, right? So you have this nested linear model, and then you apply the filter to it. That's just an inheritor of this linear model. And the next step is treating W, this connectivity, as something that we don't know. So maybe estimating a decay parameter or something that also, if you condition on the filter and the nested linear model, you can also just update that. So it's a straightforward inheritor. That's what it would look like. So maybe we depart from the linear model, have some special cases of a conjugate prior maybe, or some shrinkage priors like the horseshoe or normal gamma shrinkage, or have this spatial interference in here. And now note that these prior setups here, we can also inherit. So it would be an inheritor of the shrinkage if we want to apply that. So ideally, we want to create these classes dynamically. And a layer further, the nonlinear models here are, for example, the spatial autoregressive filter or this filter on the error terms. Of course, we can combine them, or we can also apply another step for the connectivity. But in general, so I'm thinking of this for spatial models, but this can also work very generally, and it's kind of similar to how JAX is implemented. So this could also include maybe a filter for the error terms, so have stochastic volatility, or limited dependent variables, or some other step in there. That's just a very natural inheritance structure. Now, within this OO system, we would use a functional approach, right? Because we're still quite flexible with that and extensible. So instead of having this matrix X that contains your regressors, I'd like to think about it as just a function that returns the matrix X, because maybe that's something that we adjust in the turn of sampling, right? So the idea is to use a lot of lambda functions in there. So if you want to adjust it, it's possible. Now, this is all nice and good, but to make it practical, an interface is needed. I'm thinking of first a programming interface to instantiate our objects, for example, combining them dynamically, but also helping choose priors and so on. So you have some helper functions for that, but also to work with objects, right? So maybe you want to just obtain some samples or burn some. But another nice aspect is, for example, adaptive MCMC. So you may want to tune your Metropolis Hastings sampler, and you can just do that with a straightforward helper function that basically says, hey, generate 10,000 draws and try to get an acceptance rate of 40%. And last but not least, it can help to prepare outputs. So maybe you don't want the matrix, but a Tibble, or maybe you already want to check convergence of these samples. Now, that's already a bit hybrid with this OO and functional approach. So it's kind of a chimera, but we still want to put the tail on the chimera, which is why I think a user interface would be very helpful, right? Because at the moment, this combines some weird aspects that may not be natural to every kind of language, for example, R. So a user interface that's very natural in this kind of language could just sit on top of the programming interface and link that with the language. So in R, we step from what I discussed before to maybe a formula interface. Just have this function like LM for linear models. Just have a plain plot method that does this in an R style. Or also include interfaces to Coda, Broom, ggplot, and others. Now, so much for the architecture. I hope you got the gist of it. Now let's briefly talk about the implementation. So in BSReg, I try to follow this software architecture and implement it in R. I use R6 as an object-oriented system. It's much more a classical OO system than, for example, S4. So if you know OO from C++, it's closer to that than standard R. And I use it to represent, on one hand, a range of models. So roughly starting from just a plain skeleton that has the methods and so on that we want to fill later on. Then the baseline is a non-conjugate linear model with a normal inverse gamma prior. Now a special case would be just a conjugate prior where you skip some parts, or shrinkage priors. So BSReg supports horseshoe and normal gamma. Then you may want to include local spatial lags. Another inheritor would be these spatial filters, so maybe have the combined models. And you can also estimate connectivity with it. Now, R6 is also useful for Metropolis Hastings samplers, but I won't get into that too much. But in general, the structure is also always the same. And yeah, so in between, or so in this object, again, I use a functional design. So I'm very happy for the new Lambda functions in R. Now, how to use this? There's, again, two interfaces. So a programming interface, or maybe a helper function to just set options in general and adjust this specific type, the SLX model. And maybe we say, hey, I want proposals for a distance decay parameter. So I set a proposal scale. So it's going to do it automatically afterwards. Then we want to instantiate our object. Maybe provide the data, the dependent and explanatory variables, and the options we had before. And then maybe we just want to obtain some samples and burn the first 1,000. Now, what's interesting here, because this uses R6, more kind of standard thing, and it's a state machine, the state is modified in place. What we do is we're just tracking what it does beside, but this M afterwards will be updated. Maybe now you notice this is not very R idiomatic, and you wouldn't expect it as a veteran R user. So we also have this user interface, which just looks like, hey, I want a Bayesian linear model with this and that formula. I use this data. So you could compute a summary that's all implemented. Maybe you omitted the spillover effects from local neighbors. So you estimate an SLX model. So here you just need to provide a matrix or a function that gives you back the connectivity. If you want to check convergence, which is always important for Bayesian methods, is you just call the plot method. And again, so this modification in place is in there, just it's a bit more hidden. So we can just compute more draws using this exact thing. So it's not a one-time thing. You run this sampler once, you generate, I don't know, 10,000 draws. But if you want to do it again, you don't need to discard them. You can just do it again, call it on the same object. Now I'm closing in to the end. Let's briefly talk about the application. So it's about a cigarette demand elasticity estimation for the United States. It's kind of a standard issue and test for spatial models, because there's good evidence of spillover effects between states. Right? You may go cross-border shopping if the neighboring state has cheaper cigarettes and so on. I will have a look at the effect of income. Now here we're comparing the linear model on the left and with some spatial models on the right. I think the most interesting one here is maybe the SLX model. You can see there's a spillover effect. That means the estimate is a bit lower than in the linear model. And also, interestingly enough, if you include these spatial terms, as extra parameters, and especially the filters, you get increased uncertainty. So this has very fat tails. It's not a normal posterior. Now, there's uncertainty around the spillover effects, but also around the connectivity. And Halleck-Weger and Elhorst, in a 2015 paper, they proposed to use an SLX model, so the local spatial lag, but with parameterized connectivity. So they say it should be inverse distance decay, and we estimate the speed of decay. kind of looks like this, and we can easily implement this with a Bayesian approach, and that's what it looks like. So in the left, we have again a contiguity W, basically where the borders touch, and to the right, we have 3 variants with a distance-based one. You have here delta fixed at 2 and 4, so the speed of decay is fixed, and to the right, we estimate it. And you can see that the left one is basically far off of these because it doesn't capture the connectivity as well. And you can see some additional uncertainty to the right that stems from estimating delta. If in a non-Bayesian approach, that would be fixed, and we would probably, as in the paper, they underestimate the uncertainty. There's another final point I would like to make why software is needed. So the average partial effects, it's going back in time in spatial econometrics, it's an issue, but also for the SLX model. They look like this. Sometimes they're directly given by this parameter theta, but not always, because they depend on W. And what Halleck-Weger and Elhorst, and also importantly, the spatial package do, they ignore this dependence on W. And in this case, they overestimate the spillover effects by a factor of 7. So that's quite important and an issue. So thanks for your attention. I hope I'm all right with time. You can find me on my webpage, contact me on Twitter and so on. There's also the paper, which is also available from my webpage, and this package here that you can use. Yeah, so I'd be happy for any inputs from your side.
Yes, thank you very much. It was a really interesting presentation. I'm just afraid we are running out of time a bit. So maybe you can post your questions to the Q&A section, and we can have a discussion at the end if it's possible, or you can contact Nicolas by chat or email.
Yeah, so I won't be around for the whole session, unfortunately, but if you have any comments, I'm really glad to hear them, and you can just shoot me a mail. I'll just write my mail address in the comments.
Yeah, thank you very much. So, Brian, have
Hi.
you solved your problems? Ah, perfect.
Oh, finally. Okay,
Hi.
great.
So you can start your presentation, so we are not wasting the time we have left.
Thanks.
So
Yes,
yeah,
I
try
loaded
to
the,
share.
I loaded the documentation. Do you think I can present it right from the platform, or should I share my screen?
It's better when you can share your screen. I'm not sure if it will work other way.
Oh, okay. Then I'll start sharing my screen right now. Give me a second, please.
Mm-hmm. Okay, so maybe if it will be, I don't know, you can start talking if you are able. Or if you are not ready yet, we can leave you to the end.
Oh, yes, please. still having the
Yeah.
issues with my access. Please, if the next participant can present, I will appreciate that. I
Okay.
apologize for all the
It's
issues.
fine. It's fine. Crystal, are you ready? So can I ask you for your presentation, please?
Oh yeah, for sure.
Yeah, thank you.
All right, how does it look?
Yeah, it's good. You can continue.
Okay. Hello everyone, my name is Crystal Wei and I am from Mount Royal University, and thank you user R for this opportunity to present today. I will be presenting on spatial epicism, where we created an R Shiny app for tracking COVID-19 in low and middle income countries. I have been working with my supervisor, Ashok Krishnamurthy, since May 2021, and I am excited to share our work. Before I get started, I would like to share our deployed version, which will be demonstrated later today, as well as our GitHub. So the spatial temporal dynamics of infectious diseases have received a lot of attention due to its highly nonlinear outbreak dynamics. To capture spatial temporal dynamics, multi-city models must be developed, but these models can be very large, requiring more memory and processing power than a single computer can deliver. So our motivations are to study the full spatial dynamics of COVID-19 as it spreads across low and middle income countries, not merely across a small network of connected cities. And you can think of the airports as nodes because the model relies on people moving in batches from one airport to another. And we also primarily want to clarify mathematical ideas rather than offer a definitive medical answer. So we gathered our data from geotiff rasters from WordPop. So we go to the 2020 UN adjusted population count raster. There are two native resolutions. There are a 3 arc-second resolution and a 30 arc-second resolution. So we use the 30 arc-second resolution, which is approximately 1 kilometer east-west and 1 kilometer north-south. So as you can see here, this is the Nigeria population raster, and it has 1,665,796 grid cells. So for Nigeria, the downloaded TIFF file at the 30-second arc resolution is about 4.61 megabytes in size, and the raster contains 1,156 rows by 1,441 columns for non-overlapping grid cells. So according to the CISIN, the population count grid contains estimates of number of person per grid cell, whereas the population density grids are derived by dividing population grids by the land area grids. So the 30-second arc resolution of the GPWV4 result in cells that are roughly 1 square kilometer at the equator. So the density will be approximately the size of the count, with each cell size being about 0.008, but we can round off to 1 kilometer by 1 kilometer. So for this exercise, we use the TerraR package, which is developed by Dr. Robert Hingems. So according to Dr. Hingems, Terra replaces the raster package. So the interface of Terra and raster are pretty similar, but Terra is simpler and faster and can do a lot more. If you use OS, if your OS is Windows, you should install RTools 4 before you install the R Terra package. So this is a demonstration of the image created through using this package. So people are used to the standard SRI type model where there are no grid cells. So that's the frame of mind they come in. So this is a flowchart which applies to one of these for each cell. So compartments within each grid cell This is a schematic representation of flow of individuals between epidemiological compartments. The basic idea is that transitions of individuals from previous to the next stage of the disease are seen as stochastic movements between the corresponding population compartments. And each period, an individual either stays or moves to the next compartment. So for our beta values, represents our daily rate at which susceptible individuals become exposed. And then our gamma is our daily rate at which exposed individuals become infectious. And sigma is our daily recovery rate for infectious individuals. And delta is the daily death rate for infectious individuals. So here's our retrospective analysis. So these are the reported cumulative deaths, and there are our two scenarios, which is our no restrictions, which results in more deaths over time compared to having restrictions over time. And this is based off of data from September 2020 to December 2020. So our conclusions for retrospective analysis, according to the data collected from that time span, was our simulations prove the importance of government intervention and restrictions during the COVID-19 pandemic, where we illustrated this with our scenarios 1 and 2 simulation. This simulation shows that without any restrictions, Nigeria would have experienced nearly twice as many COVID-19 fatalities, and the lack of restrictions would also have resulted in a considerably greater number of active cases of COVID-19 in Nigeria, making the vaccine rollout beginning in early 2021 overall less effective. So we know that vaccination is one of the most effective ways to prevent the spread and reduce the impact of infectious diseases. And we assume a consistent supply and availability of vaccines, which clearly any disruption of supply can have a huge impact on projections. As Dr. Fritzi famously said, models are only as good as the assumptions that you put into the model. So here are the latest numbers of confirmed cases in Nigeria as of June 15th. So for individuals to set up the simulation, the dashboard that I have provided in the chat, we can set advanced based on characteristics of COVID-19. There are boundary conditions that can be applied, so no movement from neighboring provinces, inflows and outflows, and no vital dynamics are included in this model. Initial conditions, so we have seed active cases, which are recovered, and dead data from the Nigerian Centers for Disease Control and stratified by states based on start date. So here I will show a demonstration of an MP4 video created on our dashboard. And this is over 120 days. So before I go on to the demonstration, I would like to acknowledge my supervisor, who is the project PI, Ashok Krishnamurthy, and my fellow peers who have also worked on this dashboard with me as well. All right, let's go on to the dashboard. So you can have the option of choosing only low middle income countries. Today I will be demonstrating Nigeria. So in the future, we want to have the option of being able to see simulations based solely on isolating provinces or states. And we have set default values as well, and you can have the option of testing an SVRD model or an SERD model. And here users will be able to upload their seed data. So we will do an SERD model for 2020. We'll do it here, and then we set the date here, and we can run the simulation. Oh, sorry. 1 second. Oops. All right. SRD, browse. Oh, it doesn't like me today. 1 second. Oh, geez. Okay. Interesting.
Yeah, maybe you can continue and show this later, or because it's like maybe a lot of people is trying to work with it and it happens.
Maybe, yeah.
Said.
Yeah, I might be able to use go on RStudio then and run it through there at the end. Sorry, I'm taking time.
No, it's fine. It's fine. Continue.
Here, I will just run it through RStudio. Okay. Let's see if this will be okay. All right, so here is our dashboard. So you can see the math that it produces. And here is the mathematical model that we use for density of population as well. And then because we use the SRDs, so then this model will show up. And here we have output and plot. So I can play the MP4 that gets produced here. And this is for 3 days. Well, thank you so much for your time, everyone. And I can pass on to the next speaker of today.
Yeah, thank you. Despite all the problems, it worked fine at the end, so perfect.
Yeah.
Thank you very well.
Thank you.
Yeah, I have some question here, so maybe just a brief answer. Should there be a model accounting for breakthrough infections? I personally know a few people who got COVID after 3 shots of vaccine.
So currently we are going to add another development in our dashboard, which accounts for vaccinations over time given a time frame. So stay tuned and keep updated with our GitHub.
Thank you a lot. So, Brian Fuentes, are you ready?
Yes.
Yeah.
Finally. I
So
would like to start by apologizing to all the presenters in the audience as well for any inconvenience, but I think I'm ready to roll right now.
Okay, so feel free to share and start.
Okay. Could you please confirm that you're looking at my screen right now?
Yeah, perfect. It's working.
Awesome. Now this is a package that I developed a little while ago, mainly during my free time, and it's not necessarily about spatial statistics or about the environmental modeling using spatial explicit data sets or geospatial layers, but I didn't find a better fit for the presentation. However, you will see that at the end of the presentation that some of the outputs created through this package can be used as inputs for spatial explicit regression models or any other statistical learning. So the package is called Rasta. I wrote it a little bit after my master degree, mainly during my free time. And the purpose of this package is to assist in the stratification, the spatial stratification of landscapes, and to calculate similarity metrics to strata that can be used to guide some, and also some sort of modeling of continuous and discrete phenomena. So Rasta is overall a user-informed and informative computational framework for landscape modeling. The methods in the raster package are based on the raster layer, like GOT, for instance. Also, the package allows parallel processing and raster layers being in the memory because raster uses the package Terra as the main engine, which is written in C++ and has all the bindings and is available in R. So we take advantage of Terra to do all of the geospatial analysis. And also by being an R package, Rust enables full interoperability with other methods in R. And obviously Rasta is free and it's open source. The sheet of Rasta, most of the functions in 5 groups: the landscape stratification groups, the landscape correspondence metrics, the stratify sampling, predictive model, and miscellaneous functions. And I will talk about each group next. So the spatial stratification is very simple. In practice, it's very simple. Now in theory, have some complexities because it's based on hierarchical reasoning, and also it fits from domain knowledge. So when I say it's a user-informed computational framework, means that we need to have a priori knowledge of our system under analysis and which are the controls, for instance, and how those controls are related and what is the influence that they exert on phenomena. Now, for the spatial stratification concept, roughly speaking, is an intersection of categorical layers, which are in turn derived from input layers that can be both continuous and categorical. Like in this example, we have 2 different type of variables. We have terrain like elevation, slope, curvature, and we also have climatic variables like precipitation, thermality. Then we aggregate these into classification units, and we intersect this into stratification units. So the hierarchy follows the classification unit level, and second, the actual stratification unit level. And this is with real data sets. We have for the terrain landscape factor at a local scale, we have 2 variables, the slope and the convergency index, which is some sort of a curvature measurement. We combine those two, and the combination can be performed in Rasta using unsupervised learning or cluster analysis, but also supervised learning can be performed outside of Rasta. and you create these classification units, and then you do the same for other variables. Like in this case, we have also another terrain variable, but a different scale of analysis, which is the aspect. Now it's a more coarse, spatially speaking. And we also have a categorical variable, in this case, geology units. So we perform the stratification through intersection. And the good thing about RASTA is that allows you to track the original inputs for each of the stratification units. Like units map, if you read the stratification unit 111, that means that it takes the terrain local scale unit 1, the terrain regional scale classification unit 1, and the geologic unit, the geologic. So you can trace back the inputs for each stratification units, which become really handy for things that you're going to see next. Now, in the landscape correspondence group, we have the first landscape correspondence metric, which is the spatial signature. And the spatial signature is nothing more than a raster layer suggesting the similarity between the environmental configuration or the landscape configuration of one unit to the landscape configuration of complete geographic space. So we group the continuous variables in this case. We create the classification units. We do some sort of histogram-based sampling. And then we derive some empirical functions which best describe the relationship between each variable within each classification unit. And then the user here can apply their expert knowledge, their domain knowledge, in order to select appropriate empirical distribution function, which best describes the relationship between the classification unit and the variable. Once we have selected the empirical function for each variable and predicted across geographic space, we aggregate them into a single and overall metric of similarity, and that is the spatial signature. In this case, the classification unit 1, we see 3 variables, the predicted distribution functions, the variables, and the aggregation, which resulted in the spatial signature of the classification unit 1. So each pixel in this raster layer you what is the correspondence between that specific geographic location and the environmental configuration presented by the classification unit 1 in this example. This is a pseudocode about the spatial signature calculation process, which I won't read line by line, but it's there. Now, this is another example, like a real dataset example. We have 2 terrain variables. We have classification units derived from those terrain variables, and then the distribution functions for each variable and the overall aggregation. So when you aggregate distribution functions, then you get the spatial signature, and you can compare the map of classification units and the map of the spatial signature. And if you look at the dark red color, which is the classification unit 1, it's a discrete entity, of course. It's a classification unit, sorry. And below it, you see how the patterns vary across the space according to the similarity or the correspondence between any place or any location in the landscape and those represented by the classification unit 1. So higher values, higher correspondence, basically. Now, following the hierarchical framework, and I won't go with a lot of detail because it's practical aggregation of spatial signatures, you get the landscape similarity. So when you get spatial signatures for layers or raster layers belonging to different landscape factors, terrain, climate, vegetation, geology, etc., and you aggregate the spatial signatures for classification units from different landscape factors, then you get the landscape similarity metric, which is another aggregation process and only follows the hierarchical reasoning of the stratification process. So in this example, you can see the intersection of climatic and terrain classification units give you the stratification units here. And the aggregation of the spatial signatures from classification units gives you the landscape similarity to this stratification unit. Here in this example is the 1-1, which means one terrain classification unit or terrain classification unit 1 and climatic classification unit 1, and then you get the landscape similarity. Now, these layers are very important, and you will see why. These landscape similarity layers are very important because they can guide the optimized allocation of sampling schemes. And you can follow a stratify approach. So for each stratum in your landscape, you identify which pixel has the greatest landscape similarity to a specific stratification unit. You place a point, and that point is assumed to represent or to best represent the environmental configuration captured by that stratification unit. That way, if you discretize your geographic space into multiple variables or multiple criteria, you only need one sample per stratum, and that would reduce substantially the number of samples, hopefully, if you want to collect training observations for any other model scheme. But also, these metrics can be used to train these layers can be used to train some sort of a predictive modeling algorithm, which is based on weighted average. And the weighted average in Rasta is performed using this landscape similarity as weighting factors. Now, this is some sort of nearest neighbor, not in the geographic space, but on the feature space. And, it's computationally demanding. But if you don't have enough data for your study area and you have a lot of domain knowledge and a priori knowledge about your factors and the way they interact, then it can result very efficient because you can model with very few samples and then you can get accurate spatial variability. I'm gonna go really quick about the applications. Like in real world data sets, we can perform supervised hill slope delineation. Rasta applies the concept of the self-organizing map to reduce the feature space, and then it clusters the self-organizing map. We have 4 terrain layers here. The self-organizing map derived from those terrain layers, and these are the resulting hill slope delineations. And Rasta also allows you to visualize raster layers in 3D, interactive 3D plots. And this is actually an animation or image exported from Rasta. So you can see that the 4 layers were aggregated into these hill slope delineations from summit to floodplain, which may be very beneficial for soil survey and hydrologic modeling as well. Another application is a supervised wetland delineation. In this example, green circles represent incomplete wetland delineations, while the blue ones represent complete, fully delineated wetland delineations, which will be used for training within Rasta. So Rasta allows you to obtain the spatial signature by these complete, fully delineated wetlands. And using this spatial signature of wetlands, then we can discretize or binarize the result and do a semi-automatic delineation of those incomplete wetland delineations, which are the red. You can compare the green circles, which were incomplete delineations, and then the red polygons, which were the completed delineations by Rasta. Another quick example is the disaggregation of parent material delineations. You can think of parent material as geological. So when you have coarse maps done in the 70s, 60s, 50s, you can actually disaggregate and refine the spatial detail using the landscape similarity layers. So this is the result. The white delineations represent the original delineations, and then we are comparing here the output from Rasta and the random forest model. Now, Rasta does not require training data whatsoever other than the layers that you have in your expert knowledge. While for random forest, you will need to perform some sort of random sampling, background, presence or absence sampling, whatever, and perform your modeling. Then the last example is modeling in the context that you were referring to as, but it's more like modeling across geographic space. And this is based on the landscape similarity layers too, and representative observations. In this example, we have soil organic carbon percent. The true distribution is presented to the left, while the simulated distribution or the model distribution by rasta is presented to the right. So they follow some sort of correspondence. Now, finally, rasta is already available in CRAN. It's also on GitHub, and I have a preprint in Earth Archive, and the corresponding paper will be published in our journal in this next issue, which is in December 1st, I believe. So thank you so much.
And thank you very much. It was definitely worth to wait for this presentation after the technical issues. Well done, good job. So if you have any questions, we have just a few minutes left. So I open the discussion for all presentations. Just Nicholas had to leave earlier, so if you have any questions, post them to Q&A. If not, or if you are waiting, we can wait a few seconds. But I want to thank all the presenters and the audience, of course. Recording of this session will be later available on the platform, maybe right after the session. Okay, we have one question. Sorry, if this is a naive question, but does it require polygon inputs? If you only have point data, would uncertainty be high? It's for Brian, I think.
Oh, okay. Thanks for the question. Could you repeat it?
Of course. Does it require polygon inputs? If you only have point data, would uncertainty be high?
The main inputs for the landscape stratification process are raster layers. You can also have polygons, and those polygons can be used as a reference to create the classification units. You can also have point data to validate, let's say, these classification units. But for the stratification, you only need raster layers. You don't need polygons, so you don't need vector data. Now, for the actual modeling, like the modeling of continuous or discrete data, then you need training observation for both train your model and also to validate your model. Now, if you don't have point data, but you can assign one value to each stratification unit, then you can also work with that. So it's pretty flexible in that regard.
Okay, thank you. So if you have further questions for the presenters, you can reach each presenter directly via this platform, or you can reach them by email. And after the break, you can join us for the last keynote and closing remarks. So yeah, there are no other questions. So I wish you all a pleasant afternoon or evening, depends on where you are now, and see you.
Bye.
Bye.
Thank you.
Thank you.
Bye.
Thank you. I just had a quick question of where to find the recorded talk.
This talk is when you go in the lobby of this environment. You can see your past sessions, and when you show them, when you open them, there is a view recording button.
Okay, thank you. Well, thank you so much for your time today as well.
Okay, bye.
All right, bye.